Hi, my name is Cromwell, if you didn't see the keynote, and I am a member of the Google Web Toolkit team, well, or I should say GWT team at Google. And I primarily have worked on the compiler over the years, and so this will be a talk about the compiler. And so I have two goals for this talk. One is to basically give you guys an idea of the structure of the compiler and how it works. So if you've ever just been curious, hopefully my presentation can satisfy some of your curiosity. The second thing, though, would maybe be that to get some of you out there who may have an interest actually in contributing to the compiler to actually fix some bugs or to extend it. And so one of the things you might be wondering is, do you need like a PhD in compiler theory to understand this session? And the answer is that you won't. I've boiled it down to make it fairly simple so that you actually kind of hopefully get a good idea of the basic way that the compiler works and how you can sort of plug into it. But to give you fair warning, this original session, when I gave it to the GWT steering committee privately, was about 2 hours long. And so I'm going to skip over some of the slides. Most of them are redundant, and really what you learn in the beginning will apply to what has been skipped over. Okay, so with that, let's just talk about the overall structure of the GWT SDK. I like to think of the GWT SDK as being composed of three major pieces. One is the compiler tools, and that's the GWT compiler and the dev mode. The other piece is the libraries. That's the GWT user jar package, and that's split up into pieces. There's obviously like the core, which is like the Java util stuff and JRE emulation, but there's also all of the stuff that sits on top of it, like widgets, as well as some intrinsic stuff that you never really see behind the scenes, but it implements things like Java arrays. And then finally, there's the runtime stuff, and an example of that is the Bootstrap, like the Nocache.js stuff. But today we're just going to talk about the first bubble, which is the compiler. And one of the ways to think about the compiler is that it's really composed of three parts. And it's not just a way to think about it. Actually, this is the way the compiler is executed internally at Google. There's a pre-compile step that translates the Java code and parses it off the disk into an intermediate representation. And then there's an optimization step, which we shard out to many machines. So for example, if you have 100 permutations, different language locales, different web browsers, we just farm that out to many, many machines. And then finally, there's a linking stage, GWT linkers, which brings those pieces back together into a single sort of war application. What I want to talk about basically is the optimization and precompile, not so much the precompile. This slide looks fairly complicated, but what you really just need to understand from it is that all it really does is this is representing what we do when you launch it to compiler. It reads the command line arguments, it loads the GWT.xml files, which tells the compiler where all the source files are located, like all the names of the jars, all the names of the source directories and the supersource directories of where you might find Java source. And then basically it invokes the Eclipse JDT compiler. So if you guys are Eclipse users, you're kind of aware that when you save a file in Eclipse, Eclipse like compiles it on the fly to bytecode. So we use the Eclipse JDT compiler internally to parse Java code and give us basically a compiled representation of that code, not the JavaScript, but basically like what was in it, classes, fields, methods, and so on. And so the rest of the stuff you don't really need to know, but essentially we initialize this thing called a compilation state builder, which has JDT inside of it, and that basically gives us all the JavaScript, the Java code parsed into an internal format, which I'm going to go over. One interesting thing though is this compilation of Java into some intermediate representation happens in a loop, because if there happens to be a GWT.create statement in your code somewhere that triggers some new Java source to be created, then the compiler has to loop back around and compile that again, because obviously everything that was presented to it at the beginning wasn't the complete list of source code. The generators actually added more. And because generators can generate GWT.create statements, you can have more loops. And so the compiler keeps looping around until no more source code is produced. So after that happens, we essentially have what is called an abstract syntax tree. That's what we call the Java AST. And so what is a Java abstract syntax tree? this is what it looks like. It's kind of like Java reflection. If you're familiar with Java reflection, it's just a sort of a more detailed way of representing what was in the source. Java reflection kind of tells you what the names of the classes were, and what the names of the fields in the class were, and what the names of the methods in the class were, and what the parameters were, and return types. And that's kind of what's represented in the type oracle, if you've ever written a GWT generator, provides to you. But the compiler goes deeper. What the GWT compiler gives to the GWT compiler is things that are inside of a method. It will tell us that, well, here are the methods of the class, but there's also, within the method, there's state block, and within a block there's statements, and maybe there's an if statement. Within the if statement there's more statements, and then there's expressions. So it kind of breaks the Java code down into this tree of statements. And they essentially look like this. For each possible piece of code or snippet of code in Java, there's an equivalent class that kind of represents it. The root of every bit of Java code is a J node, but then there's variables. You see a J variable up there. And of variables, there are different kinds of variables. There are fields, there are local variables, there are parameters to the function. Or you can see that there's a statement. And of a statement, one of those could be an if statement, or some other declaration. Or you could have a J method, which has a J method body, which has maybe a Disney method body inside of it. So that's the general look. And here's an example of how the compiler translates this. So here's a really simple class. It's just one class, it's called foo. It has one field called x, it has one method called bar, and it has an expression which assigns that field x of 2 plus 5. And what you see on the right is the representation that we have of that in the memory of the compiler after it's been parsed. And so at the very top, you have J class type, which is named foo. And it has two children. One of them is a field, a J field, and one of them is a method. And so the field will have pointers to the type of the field. And you have two different types. You can either have primitive types, which are like ints and characters and booleans, or you can have reference types, which point to other J-class types or J-interface types. And then underneath the method, you can see that the bar method has been translated into a J method bar, which has a J method body inside of it, which has a J block inside of it. That's this curly brace right here, which has a J statement inside of it, which is like this line right here. And that line is actually has a J binary expression. And so every operator, like plus, minus, divide, percent, all of those things, equals, are represented by a J binary expression. And basically this one in particular is a binary operation of ASG, which means assignment. And then that thing has two children. The left side is what's on the left side of the equal sign, which is this X. So that's a J field ref. And what is it referring to? It's actually referring back to this field declaration, which you see up here. Then on the right-hand side is this 2 plus 5, which is another J binary operation. On one side of it is a int literal, which is a 2, and on the other side of it is another int literal, which is 5. So one thing about the tree is the parse tree of a program, if you look at all the leaf nodes at the edges of it, you'll often find literals or variable references. And literals are things like strings, like quote hello, or 2 or 42, things like that, or a variable like x. So the leaf nodes of the tree is usually always values of some kind. Okay, so that's what the compiler sees before optimizations begin. Hopefully that's kind of straightforward. And now we're going to actually look at what does the compiler actually do to optimize your code. So I'm kind of trying to walk you through the anatomy of an optimization pass. And this is where it seems like it might be difficult, but I promise you it's actually kind of simple. It just looks difficult. There are different kinds of optimizations in compilers. There are local optimizations, we kind of just look at a statement at a time or within a method. And there are global optimizations, which basically look at relationships between classes or between methods. And so the simplest kind is a local optimization. And typically, a compiler optimization consists of one or two passes. One of the passes is usually an information gathering pass, meaning we kind of like look over a method and we look for opportunities to optimize something. So it's kind of a data gathering pass. And after we've gathered some potential areas where we might want to optimize, then we pass over it again and we actually replace those constructs with something else. The basic gist of an optimization in the compiler is essentially like a pattern match, like a regular expression, it's just a little more sophisticated. And so to give you an example, all optimizations in the GWT compiler essentially extend this JModVisitor class. It's essentially the visitor pattern. And what you do is you subclass this type, and then you execute your class. And what it does is for each one of these nodes, like JBinary expression, JIntLiteral, JFieldRef, and so on, you get a callback. And here, the callback methods are visit and endVisit. And so here's an example of one where we have an optimization called constant folder, and it looks at JBinary operation nodes. So it just does callbacks for every single operation in the entire program that's a binary expression, like A plus B. And you'll get a callback. And then it's your decision to look at that and see if you can replace it with something better. And so in this example, you can see it says, if node.getOp equals binary operator add, so if this binary operation of two variables is a plus, then look at the left-hand side, node.getLHS, that stands for left-hand side. And if it's an instance of IntLiteral, like a 2, like this one here, and if node.get right-hand side is also an instance of IntLiteral, which is this one right here, then we can do the calculation ourselves. We know at compile time that the left-hand side is 2 and the right-hand side is 5. So why don't we just add that together and replace it with 7? It cannot possibly change at runtime. It's basically always going to be 7 no matter what. And so the next statement is, okay, we've found the pattern. The left-hand side is a node number and the right-hand side is a node number and the operation is add. So let's just replace it, and you see this operation here, context.replaceMe, with a new JIntLiteral node, which basically takes the left-hand side get value plus the right-hand side. So we essentially we've chopped off the bottom of that chart there, like this right here, and we've replaced it with JIntLiteral 7. So we've made the program smaller, which is definitely a good thing. One interesting thing to note here is you see this, the first parameter of this node is a node.getSourceInfo. That's actually very important. All of the nodes in the tree actually remember the original line of Java source code that they came from. And so when you replace a node with another node that's kind of shortened it down or optimized it, you want to copy that over so that if there's a compile time error someone later, you actually will get a good error report. It says like, you know, A plus B in some class actually had an error. And this is what the result looks like after this callback is run. And you can see we've basically just replaced the, we've replaced it with x equals 7, essentially. That's what those two bottom boxes look like right here. A field ref with an assignment, and the right-hand side is a 7. So this is kind of a detail that's something you can look at when you're actually starting to contribute, but it's not really that you don't really need to know about. I'll just kind of briefly talk about it. These nodes in the tree that the compiler puts there, sometimes it wraps them with another node called Null Type or Null Type. Because what the compiler can do is after other optimization passes, sometimes it will decide that a particular class was never allocated. Like class foo, if no one ever newed it, meaning they never constructed it, there will never be an instance of it. And so what it will do is in the AST of the program, it will just replace all of those references to class foo with Null Type. And so sometimes when you get a callback, and like right here you see where it says if node.get right-hand side instance of JLiteral, sometimes it will be one of these wrappers like Null Type or non-null type. So this code is actually not correct. Really, you'll have another check in here, which is if it's an instance of non-null type, you have to call a getter to unwrap it to get the actual type underneath. And so that's just a detail. Okay, now let's talk about the actual optimizations that the GWT compiler does. And hopefully you'll see for the first time actually what the compiler does to your code. So there are many different optimizations that it does on Java. The first and most important one, the one that gives you the biggest bang for the buck, is called pruner. And essentially what it does is it starts out at the entry point of your program on module load. And it traverses the entire program based on the method calls. And so if you have a method call from on module load to method A, and then method A might call B and C, and B and C might call D and E, it basically just keeps walking those calls, and it marks them as used. Then at the very end, it says anything that I didn't reach, we just delete it, and because it's unused code. And that's basically drops most of the code that's not used in the GWT clause. So if you include the entire GWT user jar in your application and you don't run pruner, you essentially get tons and tons of stuff in your output that you never use. You never use, let's say you never use the GWT canvas class. Well, it will be in the output, compiled output, if you don't run pruner, because it has to actually make sure that you're not using it. So Finalizer does a really trivial thing. It looks for any fields that are not assigned to more than once, or any methods that are not overridden. It just marks them final, as if you had just marked them final, because there's no subtypes of it. And that doesn't do anything per se to the code size, but what it does is it helps later optimizations, because then they can actually look at it and go, well, if someone only assigned to this once, I can do some extra fancy stuff. Another thing is make call static. This can convert methods that are not static methods into static methods, and that helps later optimizations. The type tightener is one of the most expensive optimizations we do, but it essentially is one of the most important ones. And what this does is it propagates type information. Because when you're writing code, it's good practice to use the least, or the most general type that you can, so you can replace it later with another implementation. For example, if you have a method that works on lists, you typically declare the method to take a list, not an array list. And in fact, if you don't care about the fact that it's a list, you might even take a collection of T. And so that's generally good programming practice, but it's bad for the optimizer, because if it doesn't know that the parameter is actually an array list, it can't do optimizations on it like an array list. So what type tightener does is it actually looks at something like this. So if you say object O equals new foo, it will actually look at the right-hand side and say, well, that's known to be a type foo. New foo can never return anything but a foo. And therefore, the left-hand side, even though it's set object, actually is a foo. It's guaranteed. And so it actually will rewrite the code so that the declaration matches the right-hand side. And then that feeds into something called method call tightener, which says if you have like list x is equal to new array list, and then you call the add method, originally the compiler thinks you're calling list.add. But after type tightening, the left-hand side is rewritten to be array list x. So now that method call to x.add can be redirected to actually know that it's pointed to array list.add. And if we know that, then we can actually inline that method. So that's really powerful. Dead code elimination is another important optimization. This is a local optimization, similar to the one I showed you. And one of the cool things it does, it strips out like if statements and switch statements and things like that, where it knows the result of the conditional. So you can say things like, if false some code, and the compiler will just dead strip it. Or if you have x equals 2 plus 3, dead code elimination will rewrite that as 5. Okay, so let me just skip forward and actually walk you through how this works, and I think it will become really clear. So here's a sort of sample program. We have an interface called foo. We have a implementer called bar with a method called m1 that implements that m1 method. And then we have a method called bar, which extends, which also implements foo, and it has a method called m1. And then we have an entry point here, and it has foo equals new bar, and then it invokes m1, which is this here. And so the first step is, let's run Finalizer. And so since bar has no subclasses, we mark it final. Since m1 is not overridden in any subclass of the bar, we mark it final. The same thing for here. And the entry point is also marked final. The next thing we do is we run type tightener. And so you can see here that since the left-hand side was previously declared as foo, but we know the right-hand side is bar, we replace that with bar. Then we run method call tightener. So previously the method invocation here was foo.m1, and it was pointing to this one. But we actually know now, since this is a bar, that m1 is this m1 that's being invoked. And then make call static. So since m1 is final, we can actually make it into a static method. It's not polymorphic anymore. So we generate a new method here, $m1, that takes bar, which as this parameter, as the first parameter. And then we rewrite this m1 call down here, which would be foo.m1 normally, to be instead $foo m1, and we pass in the instance as the first parameter. And also we rewrite this polymorphic method here to just delegate down to this one. Well, the pruner says no one's calling this m1. This $m1 here now points to this. So we actually delete, we don't reach this polymorphic method anymore. And there's no new method allocating this bar class. So we just totally kill that one as well. And now since M1 is a static method, we actually know exactly what the method is. We can literally just copy and paste its body from up here directly down to where it's called. So we actually inline the method. But since the method is empty, basically it goes away. You're left with just bar foo equals new bar. So we kind of started out with this, and we end up with just one line of code. So just act like this has been struck away. And this is all that will be generated into JavaScript, is an allocation, plus this class up here with the default constructor will still exist. Oh, and this actual $M1 will go away because it's been inline. And so one thing is that the compiler actually doesn't stop there. The way the optimizations work is this. If an optimization actually makes a change to the program, the compiler says, something's changed. And so it loops back and reruns all the optimizations again. And there may be new opportunities, because since you deleted one of these dead methods, then maybe one of the things it referenced is no longer referenced, so it gets pruned. So the next time around, maybe that class, since it's been deleted, another class that it used to reference is no longer referenced, and that one gets deleted. And so it cascades. And what we say is that we run the compiler until we get to a fixed point. We keep running the optimizations in a loop until no more work is done, until basically we've kind of reached a settling down of modifications to the program. So that's basically the anatomy of how the optimizations work, and a simple optimization. But the compiler also has to do other things, because Java does not have the same semantics as JavaScript. And so just to give you an example, Java has typed catch blocks. You can have a try, you can have like 5 catch blocks, and they all have different types. Depending on the type of exception, a certain type of catch block will be executed. JavaScript does not have typed catch blocks, and so you have one try and then one catch block, and that's it. So how do we do that? Well, there's these things called normalizers, which rewrite the program after optimizations to make it so that JavaScript can actually execute Java semantics. And so, for example, with catch block normalizer, we collapse multiple catch blocks into one catch block, and we just put sort of an if-else cascade. So if it's an instance of runtime exception, then this. If it's an instance of array bounds exception, then this. And so on. That's pretty fairly simple transformation. JavaScript does not have longs. There's no 64-bit longs. And so we have to figure out some way to deal with that. So there's this thing called long emulation normalizer, which replaces any arithmetic that's like a plus b, where the types are longs, with calls to an intrinsic class called longlib, which has all the basic operations: add, subtract, multiply, delete, and so on. Another one is cast normalizer. This is fairly important. JavaScript has no concept of runtime types. So if you have like fx is instance of something, or a cast in Java, we actually have to replace that in JavaScript with some kind of type check. And so what cast normalizer does is it replaces instance of operations or cast operations with calls to a Java class called cast.java, which you can see in the SDK if you look for it, which has the basic checks. So like, if you say if x is an instance of array or whatever, you'll see a method in there which will be able to check to see what its type is. Another really interesting one is equality normalizer. Double equals in Java is not the same as double equals in JavaScript. And so equality normalizer basically makes that mapping work better. Basically, it figures out the cases in which you can use 2 equal signs, and it figures out the cases in which you use 3 equal signs. I think Daniel's going to give a presentation called Why JavaScript Sucks. And basically you'll see all the crazy reasons why the compiler has to work around this. Okay, so how am I doing on time? 20 minutes. Oh, it's faster than last time. Okay, and so the compiler has actually 2 stages to it. The first is it does all of the optimizations on this Java AST, which represents the program with these J something nodes. And then it has, each one of those has a type. It knows like what its class is, or if it's an integer or something. And then it takes that and it generates another tree, which is the JavaScript AST. And this is pretty much identical to the Java one, except that it's JS something instead of J something. So there's a JS expression, a JS binary operation, a JS statement, a JS method call, and so on, JS identification. And those, the reason why we do that is because, first of all, JavaScript doesn't have any types. And so we don't want to keep that information around. Second is there are things in JavaScript which can't be represented in Java. And so we need a separate AST because we need to do some optimizations that are just not possible in Java to do. But there are, let's see if I have an example here. I don't know if I have an example here, but there's a similar thing called a JS mod visitor that traverses the tree, and for each node, like JS binary operation, you get a callback. And in there, basically, you can do things like, if the left-hand side's a number and the right-hand side's a number, let me replace it with the addition, things like that. So it's the exact same concept. It's just that there's sort of a different level optimization you can do. Just to give you one example of an optimization that you can't do in Java is that you can replace all instances of the Boolean true. So if someone says x is equal to true, you can replace it with bang 0 or not 0. Because in JavaScript, not 0 is equal to true. So that saves 2 characters in the output. You did have TRUE, now you have exclamation point 0. And so that you couldn't do that in the Java AST. So there's all kinds of crazy stuff like that. Or like the number 10,000. You can replace that with like 1E4. So you go from 5 characters to 3 characters. You can use scientific notation in JavaScript. And so that's why we have 2 different stages of optimizations. I didn't get to do this in the San Francisco presentation, but since we have time, I'll briefly talk about it. JavaScript has a different conception of scoping than Java, as many of you may well aware. It's kind of crazy and confusing, actually. In Java, it's clear what introduces a scope, right? Classes introduce a scope where variables can have names. A method introduces a new scope. A try block, and in fact, even an if block can introduce a scope in JavaScript. Every curly brace can introduce a new lexical scope of variables. But JavaScript really only has 3 ways to introduce a scope. There's like global scope, there are functions, so every function or inner function or closure introduces a new scope. And crazily enough, catch blocks introduce scopes, and that's it. So the catch block is like this weird thing where if you have catch E, it actually introduces a new variable scope. And so we have to model that. And so when we translate to AST, we also create this parallel scope tree where for each function we encounter, we add a subscope to this tree. So if you have a nested function with a function in it, with a function in it, with a function in it, like you have a scope which has a parent scope, which has a parent scope. And the reason why we do this is because if there's a reference to a variable, like x, someone refers to the variable x, you ask this scope tree who actually owns that variable. And basically it will search upwards through all of the enclosing functions, all the way up until the top level window object, like global scope, to see where it's declared. And so if you have the courage to actually delve into trying to write a JavaScript optimization as opposed to a Java one, you kind of have to understand the way scopes and variables are declared in JavaScript. And so this is just a curious thing that you might be interested in delving into further. This is basically talking about like how you resolve a name lookup, basically, by traversing upwards. But I'm going to skip that because I don't really think that's as relevant to you, but I do think it would be interesting for you guys to actually know how a Java class is laid out in JavaScript. And so let's say you have a class called foo, and it has 2 constructors on it, and it has 2 fields and 2 methods. No matter what code you declare in that class, this is the minimum amount of JavaScript that's going to be output. And so you have to keep in mind, even if you create an empty class in GWT that has nothing on it, just empty methods, and you construct it, this is going to be generated in the output. So this is sort of as small as it can possibly get. And so what it does is for each constructor, you'll have 2 JavaScript functions generated. And then there's this little helper method that sets up the class called defineSeed and assigns the prototypes and stuff in JavaScript, so inheritance works. And then you basically have it setting methods and fields on that prototype. Underscore means the JavaScript prototype object backing the class. Interestingly is that I assume everyone here knows what a static initializer is in Java, like a static block, right? Static keyword with a curly brace. Or static fields that are in JavaScript, like static int x is equal to something. Well, what that translates into is a clinit function. And what this function does is the first thing it does is it overwrites itself with an empty method as the very first line. You might have seen this in JavaScript output if you looked at the output power. And then it has all of the static field initialization code there. And there's one reason it does this. the Java language spec says is that CL inits are lazily called. So the fields on a Java class, like static foo x is equal to new foo if you have a static field, that is never executed until the very first time it hits a line of code in your application that references that class, and then it lazily does it. And the JavaScript language spec says you cannot eagerly do it. You cannot change the order of that operation. And so the reason why we have this self-modifying code here is that whenever anybody refers to the class, we insert a call to the CLinit function. And the very first thing it does is it changes itself into a no-op. And then it has the initialization code. The second time later, somewhere else in the program, if it hits it again, it calls the CLinit method again, but that time it's an empty method. It basically doesn't do anything. So the class doesn't get initialized twice. And finally, because you can call object.getClass on any thing that descends from object, we have to preserve the runtime type, right? Object.getClass has to return a class literal. And so every class that's translated will actually generate a top-level variable if you look at the source of a non-obfuscated GWT build, and it'll be something like foo_classlet, and then there'll be a method called create for class, and you'll see the package name, the name of the class, a reference to the superclass, and some number that represents the class's type. And so just keep in mind, this is a bunch of boilerplate that's generated for every type that you create. I'm going to skip over the JS optimizations and normalizations and talk about code splitting a little bit. How many people in the audience use code splitting, by the way? That's good. Okay, so code splitting kind of seems like black magic. Like, how does it work? Earlier I explained that we have this thing called the pruner. And what the pruner does is it starts off at the entry point of your program, and it just traverses method calls, like A calls B, calls C, and so on. And we just keep following that chain until we can't hit any more stuff, and then everything else is deleted. Well, a code splitter essentially works like that, only it stops when it sees a run async split point. And so you start at the main method, and you go A calls B, so we go into B method, B calls C, we go into C method. C calls gwt.runAsync, and then there's a callback with some code in it. We stop. And so what the code splitter does at that point is it treats all of the code that's behind a run async split point as dead code, and it all gets pruned. It's just gone. And at that point, we write out the initial split point fragment. That's the initial thing that's downloaded. It's everything that's reachable from the on-module load function. And then what we do is we go back and we start again in the pruner, but this time we start at all of this GWT run async points as if they were the initial entry point in the program, and we follow the chain again. The callback calls this method, which calls this method, calls this method, and we stop when we hit a run async point. Then that is written out as like 1.js, split point 1, and so on. The only caveat here is that if there's shared code that's shared between more than one method, that actually has to go into what I talked about in the keynote, which is the shared fragment or the leftovers fragment. Let's see if I got a visual representation of this. And so this is a picture of kind of what this would look like. The first circle at the top is traversing everything from one module load. The circle represents traversing everything from a run async split point. This is code that's exclusive to that split point, not seen by anybody else. And likewise, there's another split point, feature B. But they both refer to this class called common AB, so they both reference it. And so in this Venn diagram, this part right here goes into the leftovers fragment. It's alive in this circle, and it's alive in this circle. And so we take the intersection of those two sets of live code, and we compute the shared code, and we write that out as the shared library. And that's basically it. I mean, there's a lot of details in it that make it more complex than it really needs to be, but at a high level, it's really just dead code pruning, where you just treat the run async split points as both the end of a program, and you can't reach beyond it, and as the beginning of another program. And so, how much time do I have left? 12 minutes, okay. So, the final thing I'd like to mention is not linking, because some of you have written linkers. There's good documentation on linkers already, so I don't really want to go into what they do. But you probably do know that the job of the primary linker is to generate the nocache.js script. And so you have things like the iframe linker, the XS iframe linker, the selection script linker, and so on. XS linker is another one. And they basically generate the nocache.js script. But maybe you've wondered, how do we actually generate that nocache.js script? What goes in there and how is this computed? And so one thing I thought would be interesting to do would be to kind of talk about this. And so one of the things GWT does is that you have different axes of permutation variables. You have the browser user agent variable, i.e. Safari, Firefox, and so on. You have locale permutations like German, English, Chinese. You even have logger permutation axes like logger level. And that can explode very quickly. If you think about the number of possible permutations, it's basically m times n times each axis, right? And the GWT compiler actually does not generate an n by m and so on explosion. It actually is kind of smart and knows how to collapse permutations. But one of the things it does do to generate the bootstrap code and not have a really giant nocache.js file with all the possibilities is it first constructs a tree of these variables, kind of like a decision tree. So you start out at the root, and let's say just for the browser, you have two decisions. You can either be Safari or you can be i6. Then the next thing it does is it pivots on the next permutation variable. So you can either be English locale or German locale, and then you can have further things. So it constructs this tree. And so one of the things about the tree is that sometimes you'll see duplicates in the tree, right? Like some of the nodes will collapse at the endpoints. The JavaScript code that's been generated for that set of permutation variables would be identical to another one. It'll have the same MD5 hash, the same .cache.js file name. And so in that case, it actually collapses those two tree nodes into a single node that basically has the two possibilities and the same file name that would load for it. And after it does that, it will construct like a sort of multi-dimensional array of all these possibilities. And if you ever looked at nocache.js, you'll see this. And you'll see like an array where like the keys of the first dimension are like the browser user agent, and the keys of the second are like locale and so on. And then the right-hand side of the array is essentially the file name, to load up the cache.js. And so, what more can I say about that? If you look at the linker, there's this thing called Permutationsutil, and that will kind of show you actually how it does it. But I just thought it would be interesting for you guys to know a little bit about that. Uh-oh, I'm getting an update. No. Okay. Okay, should I talk about overlay types? You see, okay, we're almost done. Maybe I should talk about overlay types. How many people here have written an overlay type? Something that extends like JavaScript object. Okay, cool. So this will be valuable. One of the things about overlay types is that they do not generate this boilerplate. They don't compile. So back here, see if I can find it. I mentioned that every single Java type you create, this gets dumped into the JS because you have to have a constructor, you have to have a CL in it, you have to have a class literal. And so basically that will not get stripped. And so that's basically just like extra bloat. Overlay types are different. You can have like 10,000 overlay types and it won't add a single byte to the output. It only adds basically based on the methods that are called. Whoops. And the way it does that is that, first of all, overlay types do not have any prototype. They don't have any constructor backing them. They are really just almost like C macros in a way. And what the compiler does is when you have a method on a JS overlay type, it actually turns it into a static method. And so there's no this pointer, there's just a parameter. So all overlay types essentially are just utility classes with static methods on it, even though they appear to have methods on them and not static methods. And the reason why that's one reason why overlay types must be final. You cannot overload or override a method on an overlay type because we turn it into a static method. There is one case though where the compiler has to insert some boilerplate. And that's the case where you have a Java interface that has two implementers. One of them is a regular Java object, and one of them is an interface. And so when you try to dispatch a method on that interface, like interface variable.foo, the compiler actually has to put what's called a trampoline. It puts in code that's sort of like what you see here. It says, is the variable that you're trying to invoke the method on an instance of a JavaScript object? And if it is, it inserts a call to that static method, which has the Disney method in it. Else, it actually invokes it like a regular Java method. It just calls .foo on it. Because JavaScript objects do not have any prototype. And so you can't just invoke x.foo. You actually have to call the utility method that the compiler has translated it into, because it's just, again, it's just a static Disney method. So that's basically how overlay types work, and maybe you're always curious, like, why don't we allow you to subtype them with, polymorphism? That's why. So that just about covers the presentation. Now I'd like to see if anyone has any questions. Just before I end, though, I'd like to say, remember to go to GWT.create/agenda and vote for the session, and let me know how you feel about it. Also, I'd like to say that if you are interested in contributing anything to the compiler or learning more, learning how to do stuff with it, please go to the workshop that teaches you how to contribute patches to the GWT SDK project. And now I'll take some questions. First.
I just wanted to like to know what were the motivations behind the choice of the Eclipse Java compiler?
Let's see. I can answer that two ways. One is I don't know all of the motivations because I actually wasn't on the GWT team at the time that they made the decision. But I can infer what the decision was. Is that back then Java-C, the Java-C compiler, ideally we would just base off the Java-C compiler that is in the JDK. Back then it did not have an API for getting a parsed representation of the program. It would only give you bytecode. And now it actually has a thing called the Java model, Java language model. So there's like a way to actually have the compiler give you back what we get from the Eclipse JDT compiler. And so it's kind of more like legacy that we still use it. There was another question?
Will there be a book about the internal architecture of GWT, and especially these questions?
So the question was, would there be a book about the internal architecture of GWT? There's not anything planned, but now that you've asked about it, maybe there's some publisher out there who would see this presentation and would like to talk to me about it. I would say though that the video will be made available, and there are some past videos that we have done that are more detailed than this, that walk you through almost like how to write at a line-by-line statement. There was a 2-hour-long one that was actually done last year. Is there another question?
Yeah,
you good?
Just curious, because you're going to implement the lambdas, right? So how does the actual architecture fit? Is that a big effort to implement the lambdas?
Yes. So the question is implementing Java 8 Lambda stuff. The architecture, was it a big amount of effort? And actually it wasn't. I've actually finished implementing the Lambdas already. I don't know if you follow me on Google+, which is plus.google.com/+Ray Cromwell, but I actually detailed how it was implemented. And it's actually fairly simple. The new Eclipse JDT kind of has a new node called Lambda expression and another one called method reference. And what I do is when I encounter one of those, what I do in Java code is I translate it into an anonymous inner class. And so the rest of the compiler needed no changes. I just see a lambda and I just generate a J class type in the node, the AST tree that I showed you before, and then everything else works. It's not optimal though. The ideal thing would be is actually to represent it as a JavaScript function closure. And so first step is correctness, making everything work. The next step is actually to kind of leverage the underlying JavaScript virtual machine. Was there another? Right there.
You're generating GJS nodes and you're creating source info. What's it supposed to point at? Because I screwed that up.
Typically what you do is if you are taking one node and you're replacing it with one or more other nodes, you just point it at the original. But if you're creating synthetic new nodes, then there's a source info node called synthetic. And the reason why, that's a very important question, because if you go to the super dev mode session later that talks about the future of dev mode, one of the really important things we're relying on is this new thing that browsers support called source maps, which is a JSON file that says, like, for each chunk of Java code, in the original source, it became this chunk of JavaScript code in the output. And what that allows you to do is to reverse map JavaScript back into Java. So if you open up Chrome and you go into the DevTools and you set a breakpoint, actually you see Java code in the Chrome DevTools. Likewise, if you get a stack trace exception and you want to deobfuscate it back into a real Java stack trace, the source maps actually give you really good fidelity. You can get a full, nice stack trace back, even if the optimizations have really mangled the code up. And so when you're doing these things, preserving that source info node correctly is very important. Otherwise, you might get nonsense when you actually try to when you get an error out of the compiler, or if you're actually debugging. Maybe I can write a blog post on the proper way to do that, but thanks. And over there?
Why does compilation take such a long time?
Very, very good question. Okay, I have 0 minutes left, but very quickly, GWT is a whole world compiler. It basically, every single time, it loads the entire source of your entire program in, compiles all of it, even if you only changed one class file. We did a presentation in San Francisco on this, but unfortunately they're not here, where we re-architect the compiler to make it what's called a modular or incremental compiler, where basically we compile, once we compile once, we write out the results to disk, and then if you change a class later, we only recompile that one class and re-optimize based on that small change. And so it should be very possible very soon for a recompile to actually take on the order of like 3 to 5 seconds, in draft mode especially. In fact, at the keynote in San Francisco, my talk in San Francisco, in the other room they were giving the other talk, and when he actually showed this new incremental compiler in progress, the applause was so loud, I had to stop. I could hear people just screaming in the other room about the compile time improvements. So compile time improvements are coming, and that's all I have to say for now on that. With that, I think I'm out of time, so thank you all very much. Remember to rate the session. Have a great conference, and if you have any other questions, feel free to come up and bug me. Thank you.